Hello. So yeah, I'm Sammy. It's very cool to be back in security. It's been a lot of fun, and I look forward to sharing the problem space I've been in for about the last year. My co-founder is Professor Gabriel Palmer from the George Washington University, brilliant OS researcher who decided to jump on board a few months ago after reading one of my papers on this. So let me start with a story. If it loads, I'm running in the battery saver governor, so it's going to be pretty laggy. So a couple of years ago, I had a company called Backtrace. We got owned. One of our build servers got owned. And, there was an animation, I guess. Oh, very cool. So we had a Jenkins misconfiguration, and Log4Shell was just announced. It was a build server. It was definitely an oh shit moment given some of our customers. And we actually, even though we had an EDR solution and we had other measures in place on the system, none of them really were alerted us to this actual breach. And we became a statistic. This required a lot of manual forensics work. We had to determine if any of our builds were impacted by this. We had to determine if any IP was potentially stolen. We ended up spending many hours on this, re-imaging the machine and patching the issue so it doesn't happen again, and the misconfiguration. But the sad thing is, it left a mark on me, because even though we were using kind of the industry standard EDR solution, there was no detection. And more importantly, I couldn't figure out the scope of this breach, right? I could figure out, okay, were my builds impacted? But I couldn't figure out if any IP was exfiltrated. I couldn't figure out if there was still a persistent threat on the system. It was frustrating. And so many years later, I decided to revisit this. So I recreated this scenario, but I created a generic RCE bug. And I made sure that the RCE was taken advantage of in a way that, some of the modern EDR, container, runtime security, yada, 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 whatever they call themselves these days, would actually detect these attacks. And really the idea is to figure out, okay, if this attack was detected, what information could we have gotten? Here are two very popular solutions in the market today. What the attack sequence actually looks like is there's some bug in a CGI bin script, which then allows me to launch a reverse shell. And then from the reverse shell, we actually drop a rootkit, and then we do a whole bunch of stuff from the rootkit, including accessing confidential data, exfiltrating data, et cetera, et cetera. And this is what these two solutions provided on a Linux system. And it's not much. So pretty much, I get a snapshot of the process tree at the time of detection and not much else. And this was quite disappointing. So first, before diving into this problem, let's talk about, the evolution of intrusion detection, kind of the first generation of IDS solutions. When I say IDS, I'm bucketing in EDR. With all the security tooling out there, they all evolved to consolidate more and more of their capabilities. Then you had IPS solutions get developed, and kind of EDR brought that into play in the cloud environment, and a whole slew of features, anti-malware, et cetera, et cetera. Over here, I'm starting with a classical IDS, WASA, which is a fork of OSSSec. OSSSec consolidated a lot of critical processes that older security tools used to do. So way back in the day, you had the Unix COP system, which did basic integrity checks and vulnerability scanning on Unix systems, and Tripwire got developed. That became a company. WASA kind of consolidates this, presents it in a nice dashboard. So for example, it'll do log analysis and log collection. And all it'll do here is monitor a bunch of log files for changes, and then pattern match against those log files. right? Nothing terribly interesting. So for example, over here, there's a rule that says, if this is a syslog monitor, if we see the pattern authentication failure or failed bad SU, trigger an alert, user, missed a password, yada, 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 right? And then they do similar things for application logs, like a web server, similar things for audit. So audit is a mechanism, in this case, provided by the Linux kernel, which provides an audit log of important events from a security perspective on the Linux system to be able to provide accountability for those important actions, right? And there's an interesting history behind that too. Sorry, we have 30 minutes. So, let's see. Then you have SCA, so, checking the security configuration of your system. Do you have any weird security settings on your system? So here's a simple rule, for example, that'll check if a proc setting is set to a specific value. If not, it'll trigger an alert, right? So nothing terribly interesting. There's also malware detection built in. There's rootkit detection, so very basic things like, for example, checking the presence of certain files that are known to be associated with known rootkits. And then finally, FIM. So back in the days of Unix COPS and Tripwire, those were driven via periodic checks, a cron job, et cetera, Kernel facilities were provided in Linux, first iNotify, then FA-Notify, that a lot of these products end up using. iNotify is quite popular for these suite of products. The challenge is this doesn't scale. You can't really monitor everything on your system. It's whitelist oriented in the case of iNotify, and then you really don't know who is responsible for changes on your file system. So it's limited utility. FA-Notify was later introduced, which fills in the gap there, provides mount level visibility, and has a lot of other cool features. Like you could actually do access control in user space leveraging FA-Notify. So this was originally developed for antivirus products. Some of these IDS tools are starting to provide FA-Notify backends. Long story short, though, pretty much all the tools in this space, in this what I call the first generation of IDS tooling, are just doing pattern matching across different data sources, which contain a sequence of discrete events, right? And that's effectively what all of them are doing. So, Datadog has done a lot of interesting work in runtime security monitoring. And one thing they point out, and this is pointed out many times in the literature, that ultimately your runtime monitoring technology is only going to be as good as the data that it has access to, right? The runtime data has access to. So a lot of folks started moving to and differentiating by providing increased observability into the behavior of an operating system. And we'll dive into that. So first off, with audit, for example, let's say I wanted an alert on a Linux system if any connection was made to port 31337, for example. This is actually a typo. It should be port 31337. So if I use audit, there's no way to actually poke into the internals of a socket and extract what the IP address was as a filter. So we're effectively going to have to log every single connect. You can imagine on a heavily loaded system that becomes extremely expensive. And audit is also blocking, meaning if the audit daemon is not able to consume those log entries fast enough, then the system call will block. So it can be pretty expensive. Modern IDSs, so I'll take over here, I'm going to pick on Sysdig Falco for a bit, are able to do a lot of this filtering in kernel space. So over here we have a rule that says, okay, if you have an event type called connect and the return value is greater than 0 and yada, 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 trigger an alert, right? So that works around that limitation. So in the early days, a lot of IDS systems and security products in general and antivirus products started to hook into the operating system kernel, initially primarily through system call interpositioning. This was a technique that was quite popular in the world of malware back then, even before this stuff was introduced. And these security products started leveraging it. And so by being able to hook into syscalls, you are able to get almost complete visibility into the system. Back then, things are a little bit different now. But back then, it would give you almost complete visibility into the system. System calls are how your applications are doing anything privileged on a system, or anything with a meaningful side effect, whether it's writing a file or sending a packet. There are some exceptions, as some recent EDR vulnerabilities demonstrated. So there were a few other approaches as well. So folks wrote modules, netlink modules for Linux, kprobe and perf events were introduced, but there was limited flexibility. The other issue is that system calls just aren't enough. And so further evolutions needed to happen as to the underlying data source for these intrusion detection systems. So first off, system calls and arguments provided to them don't provide sufficient context. So for example, if you wanted to implement some security policy based on the path provided to the open system call, you can't trust that pointer. It's entirely controlled by user space. It's also ambiguous. I'll give you an example from the real world. So this is a popular, runtime security product in the CNAPP world, and it has a rule to detect attempts to read etc shadow, right? So the rule specifies if you see an open syscall with read and the file descriptor name is etc shadow, trigger an alert, right? Well, the challenge is people can just use relative paths, right? And all of a sudden this rule doesn't get triggered seriously. And this is a fairly popular product among the first too. And so yeah, you could have symlinks, you could have all sorts of things. We'll get into these evasion techniques shortly. They're not enough. The other issue too is they're inherently racy. Right, so Robert Watson back in the day actually published this back in 2007, and he demonstrated that pretty much all system call wrappers are vulnerable to tuck2 bugs. Even modern kernel technologies that power EDRs are vulnerable to this too if you're relying on user memory. So that's a fundamental issue, which again we will revisit. He demonstrated this flaw in systrace among other popular syscall wrapper solutions back then. The other thing is in the modern day, you also have synchronous system call facilities on Linux like IOUring that are not operating at the system call boundary. You could do really crazy shit with IOUring. You could chain a bunch of ops to each other. So I could have a full web server written pretty much entirely in IOUring. You can open up a file, have that descriptor passed to another IOUring request or event, and have that then perform the actual read for you, right? And so in that case, there's no actual syscall being performed in the context of that user space application. And so again, hooking at system call boundaries is insufficient. There were other improvements. I'd mentioned kprobes. Kprobes kind of improve the situation there, but not entirely easy to use either. In general, kernel modules are hard and it's high stakes. So first off, the kernel module itself is likely developed in C, a very unsafe language. Bugs happen, and the kernel, the security product itself, which has a kernel module, can be an attack vector itself. And there have been many cases of this. And given the fact that it's running in kernel space, systems can go down, data is lost, or worse, right? The other is just a maintenance overhead. You have to recompile the kernel module for different kernel versions as new facilities are introduced, whether it's a new syscall or ABI changes. And then last but not least, it's kind of inconvenient that users have to trust some proprietary binary blob, right? Especially from a random startup. So let's talk about kind of, the latest runtime monitoring technology used by a lot of the new EDRs, and that's eBPF. eBPF provides a safe runtime environment for writing kernel code. This is, of course, assuming eBPF itself is secure. There have been bugs found in the verifier. Trail of Bits has actually done a lot of cool work in eBPF and formalizing the verifier, among a whole other slew of things. So just to show of hands, to figure out timing of this, who here has not used eBPF or written eBPF code? Or okay, cool. All right. Speaking of blasts from the past, I actually worked on this stuff, close to 20, 25, 26 years ago. So BPF was introduced in 1992 as a better approach to analyze packets from network interface. And it had two key innovations. One is a better buffering model, and then two is efficient kernel space filtering. So a lot of applications at the time either had to do filtering in user space, meaning they would have to copy the data from the kernel into user space, figure out if they care about that packet and drop it. Obviously highly inefficient, right? You did have kernel space filters back then, but they used a tree-based representation, which was very inefficient for modern machines. There was a cool quote that I removed, and it's right around here. It's like the design was a great fit for the PDP-11, but it's not a good match for modern 16 megabyte Spark stations. So they introduced BPF. The packet filter itself introduced, it's a very simple register-based machine with a stack, and they introduced bytecode that could be used to basically evaluate a function which either return true or false, right? So now let's fast forward to Linux and Alexei, who developed eBPF. So actually, he had a grander vision for eBPF to begin with. And he had encountered a kernel bug and realized he couldn't even trust the C compiler to generate correct code, right? And so he experimented with the idea of, hey, let's have a safe bytecode that we can use in a kernel. And after reaching out for advice, basically people told him, look, this is crazy, unlikely to be accepted, and they kind of narrowed the scope and initially focused on networking use cases, primarily software-defined networking, load balancing, among other things. So later, Daniel Borkman joined Alexei. They finally were able to merge it into the Linux kernel, and it kind of blew up from there. So they had spoke to Brendan Gregg pretty fairly on. Brendan Gregg, who is one of the main champions of dtrace, agreed this is the coolest technology he's seen in terms of enabling visibility into the internals of an operating system. So he agreed to kind of support it. So after the networking support was merged in, they ended up introducing kprobe support, and it blew up from there. I mean, today you could actually even write a fucking scheduler in BPF. That's nuts. That's really, really powerful. So this is a cool comic from Isovalent. They were one of the first, eBPF-centric, eBPF-focused startups. And the long story short, eBPF is super cool because now if you need more observability features or some custom behavior in the Linux kernel, you don't have to wait to get your patch merged in, which can take years and potentially a lot of drama, right? You can write a BPF module and deploy it within seconds. It's that easy. So it's pretty cool. The way BPF works is similar to classical BPF in the Berkeley packet filter example, the paper that I mentioned earlier. You have a bytecode that gets loaded into the kernel. It does some verification to ensure that bytecode is safe. And then it compiles that it jits it into native code. And then that gets executed in the kernel. There are all sorts of program types that you could write today, and you could hook into all sorts of things. So kprobe is one. More recently is Fentry. You can literally hook almost for free into any function entry and exit in the Linux kernel. That's incredibly fucking powerful if you care about observability. There are some annoyances to it, which we'll get into. So typically, the way it works is you will write something in what is known as BPF, a program in BPF-C. This will then get compiled down into that bytecode, and then you have a loader. Actually, I think I have slides for all of that. So this is what an example eBPF program that will hook into sysinter open syscall and just print out the PID, the path being open, a whole bunch of other stuff. So this is code that will actually get executed into the kernel. So then that gets compiled using Clang as specify the BPF target into this object file. And then you either write your own loader, or you could use BPF tool to load that object file into the kernel. So now the kernel will do that verification step. If it passes, this will start running, and you get this output. That's pretty incredible, right? So BPF does make things easier, but it's not easy. And I think we could have a whole presentation on kind of the pitfalls of BPF from the perspective of maintainability, the perspective of performance, et cetera, et cetera. I'm not going to get into that, even though that's been my life for the last year. I just want to focus, for the purposes of this talk, on the limitations and pitfalls of BPF when you're writing an observability product where missing important data is the difference between being owned and not. And some potential mitigations. So first off, a lot of security products today that leverage eBPF. How am I on time, by the way? Okay. A lot of security products today that leverage eBPF are still doing system call interpositioning. So all that crap that I mentioned about system calls are insufficient still apply. eBPF is not a magical solution to that. Here's, again, a very popular EDR product that still relies on syscall interpositioning, and it's pretty disappointing how easy it is to evade almost most of its rules, I would say. For example, I'd shown that rule earlier around reading sensitive files, right? Okay. So if I just create, they also have another rule in there, by the way. So, first thing you think is, oh, what if I create a symbolic link or a hard link from, file poop to Etsy shadow, right? So they have another rule to detect that. Okay. So, what if I create a symbolic link to Etsy system D, leverage relative paths, blah, 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 shadow A, this actually evades the detection rule of the product, right? It's even sadder than that. What if I symbolic link / Etsy shadow? That also evades the rule. It's sad. So if you're building a security product, don't use arguments from user space, and I'll get into, there's actually even more reasons than that. Try to leverage kernel objects as much as possible. Work with inodes, work with file objects, work with dentries, work with struct path. Don't work with user strings. And there are ways to mitigate this too by being intelligent around inode tracking and inode axes. The challenge with symbolic links is they are by definition just arbitrary strings. It's also a demonstration of why pattern matching sucks as a basis, in my opinion, for intrusion detection. The other thing is user memory is not always available. So up until recently, a majority of BPF hooks were not sleepable, meaning you couldn't page fault, right? So for example, over here we have a simple BPF trace script, which is hooking into sysinter exec VE. and we're going to print out and this is a system call that will execute a file on the system, and we're going to print out the file that we're executing. Pretty simple, right? There are a lot of detection rules in IDSs today that match on this, right? For example, in the RC example I gave earlier with netcat and the reverse shell, they'll have a rule that says, okay, if user bin netcat is invoked and it has a -e argument, then trigger an alert, right? That's how they detect reverse shells. Let's ignore the fact that if you copy netcat to the file XYZ and run that, it wouldn't be detected. But anyhow, so if I was to run netcat in this product, with this script. So over here we have BPF trace, right? And we run the actual script. Whoop. I don't know what's happening here, but anyhow, let's go here. Oh yeah, it's actually here, my bad. So I run BPF trace here, we attach the probe, I run netcat, and we see, okay, it managed to print out the file name, right? But, over here I have a custom launcher, which will do a bunch of things, and then execve netcat, and we could see now the BPF script is unable to access that file name argument. So all we did here is ensure that the page is not mapped. So you could flood your TLB, and the BPF script now will be unable to access that memory, and you've successfully avoided any kind of rule that involves that user memory, right? In this case, it was as trivial as calling madvise. And if you want reliability in a production environment for research purposes, you probably want to take more aggressive measures. The good news is there are now sleepable BPF programs that do cover a lot of these hooks. Which will make this easier if for some reason you do have to access user memory. Many security products have yet to switch to them though. The other issue is, I'd mentioned earlier that things don't work at system call boundaries anymore on Linux. So for example, over here, if I do sudo cat etc shadow, that rule gets triggered, which says, hey, that rule detects if the OpenSys call was made with read permissions on etc shadow, right? It gets triggered, fairly trivial. But now if we instead use IOU ring, so we're doing the open and the read entirely in IOU ring, it doesn't get detected, right? And this is still unaddressed. It's been known forever and still unaddressed in a lot of these syscall-centric IDSs. There are ways to properly support IOU ring. Tetragon does it. We're doing it, so on. And then last piece is tuck-to bugs and race conditions. So, Robert Watson first discovered this back in 2007. It's kind of had a reawakening in the world of eBPF because, yes, eBPF applications which read user memory are susceptible to this. So, for example, over here you have the kernel potentially doing a check on a path name. Maybe it's malicious. This could be the BPF program. Initially, it could be set to a non-malicious value. And then before that value is actually used, by injecting delays in user space into the kernel, for example, introducing contention, there are many other things you could do, especially if you also have access to BPF. It can overwrite that value with whatever malicious value was intended, like changing the path. For example, that path isn't susceptible to this from a.exe to etc shadow. I note the paper here. They go into a lot of detail. It's pretty cool. So anyhow, long story short, system call interpositioning is insufficient. You should use deeper kernel hooks. You can pretty much hook into almost any function in the kernel, with some constraints around inlining, et cetera, and so you can work with kernel objects. A lot of IDSs don't do this. The other challenge is BPF programs must be bounded both in their CPU utilization and their memory utilization. And a lot of objects in the kernel will consume a lot more memory than may be available to you in BPF. And that represents a challenge. And unless you design for that early on, it's difficult to tack on, your application leveraging BPF later. For example, looking at the same popular EDR solution, they have a rule that says, okay, a file was opened in a way that indicates a potential path traversal. Path traversal bugs are fairly common, or were fairly common. So the idea is if you see an open read syscall or an open fail where the path contains the pattern, ... /../, trigger an alert, right? Pretty simple. And it looks like it works. I did modify the rule here because it excludes anything called, bin bash or bash. So, for research purposes, if you rename an executable to bash, it'll also evade a lot of these rules. But anyhow, I cat, etc password using this relative path, and we get the alert triggered. Okay, so again, this is nothing like really crazy technical, They use, BPF has limitations on how much stack memory you can use. You can't dynamically allocate memory. Generally speaking, in BPF programs, you're going to work via map data structures in order to share data back to user space, right? And generally, a lot of larger data is stored in these map structures. So over here, what I do is I have now 1024 ... right? And then etc password. The path is so long that it won't fit in the buffer of this IDS solution, and so it doesn't trigger the rule at all. And what's even worse is the fact that there's no stat or anything that tells me, oh, an event was missed because the file path was too long, right? So again, design your programs with that in mind. There are ways to work around that. For example, a very simple thing is there is a ring buffer abstraction that allows you to stream data from BPF applications to user space. And that's something you can leverage. The rings can be large. Other issue is BPF programs cannot block the kernel. And this is actually the biggest issue with BPF as the data source for a lot of modern security tooling, right? There's no way to exert back pressure. So let's go back to audit. The way audit is designed, if a system call is made that should be audited, and there's no more buffer available there's a ring buffer in the kernel that stores all these entries, which then ends up getting read from user space. If there's no room, then it'll just block the system call. So the system will slow down, ensuring that all the audit events can be read, right? So ultimately you have, and by the way, this is all configurable. You could configure it to drop events. By default, it will block. And you can even configure it to crash the system entirely if those buffers are full. So long story short, audit will make strong guarantees around data loss, right? And if you've worked with databases, et cetera, these are some of the guarantees that you need when you're doing things like journaling and walls, right? With eBPF, again, you cannot block. So if events are generated faster than they can be consumed, events are dropped, right? So Valley Cybers did an interesting literature survey on all sorts of attacks that you could do on eBPF. One of them is simply resource exhaustion. So over here, we have a rule similar to that shadow rule that pamconf is read, trigger an alert, right? So you cat it, and then we get this alert, right? Everything is good. Now I run exhaust. It's also able to open up etcpam.conf, but no alert is generated. So what this application did is it launched a thread and basically flooded that BPF ring buffer with a bunch of open calls, right? And the open calls, in this case, the way this IDS is configured, don't even have to succeed. So you flood that buffer and then you perform your open call. There's no room in the buffer. It's as if it never happened. So unfortunately, this is there's a lot of other approaches. He touches on some. There's a whole bunch more, right? But the last one is very interesting to me because it's a fundamental design principle of BPF, right? It's a fundamental limitation. There's no obvious way to exert back pressure. So anyhow, all of this is kind of a big digression. I want to go back to when we got owned, right? So again, we got owned, and I couldn't figure out what was the scope of this security incident. Not only did detection fail, I couldn't with absolute certainty, or with high certainty even, determine the scope of the incident, or at least figure out what didn't happen on my systems, right? So the reason for that is, remember I showed you the first generation of IDSs, they just pattern match on a bunch of data sources. We're still doing that, right? We're still doing that today, except, now we have more kernel level observability and more events. It's simply insufficient. And then certain things like file integrity monitoring, et cetera, still to this day tend to be whitelist driven due to performance. So is there a better way? That's, kind of the journey I started, a year ago and, prototype this. So, I asked myself, what if we could track every meaningful system interaction? What if we had a system that was performing enough that we could track every single read system call, write system call, every single connect, accept, packet being sent, et cetera, right? What could we do with that? What if we could actually store those interactions? What if I could always go back in time and ask, what happened on my system? Last week, Joe Schmo was kind of shady. What did they do between this time and that time? Oh, my source code got leaked. Right? Did anyone access that source code, across my fleet of machines? So, again, the first question is, if we could track and we could store, is it actually useful? And it is. It has a lot of interesting use cases. So, over here, for example, I have an executable called lol, right? And this is running on a build server. And what you have here is a provenance graph generated from real data on the system that tells me what influenced lol, right? And I could see every single file. So I always loved this, even though C is not, going to continue being as relevant most likely in the next 20 years, but plenty of other compiled languages. But you can see every stage of the compilation process. So you can see GCC here, calling into the C compiler, all the header files actually being read, including the source of lol, the assembly being generated, the object file, et cetera, et cetera. And now you could ask all sorts of interesting questions about the provenance of your actual builds. Again, assuming the data backing this graph is itself not compromised either. And that's a whole other thing around tamper evidence. But assuming that integrity is intact, I can ask questions like, hey, was any source code in this executable not originating from my Git repo, right? So it's pretty cool. That's a cool use case for it. And there's been a lot of interesting work in literature as well we'll get into. The other thing too is if you're tracking every single interaction, we can get a lot more useful data than a process snapshot, right? If an attacker was to go in and inject a backdoor through cron tab, for example, that's now not in the process tree, it gets executed later. None of these solutions are really going to give you anything interesting. Maybe they'll get an alert that cron tab was modified unless one of these many other mitigations were used, right? So you can go from this to this, right? And there's other cool stuff here, which what I won't get into is actually including user space context in that data. Like which HTTP request was your application handling, and what were the contents of the HTTP request when this policy violation and alert was triggered. And yeah, we're still in the early days, and we'll get into, I'll get into the mechanics of this in a separate talk and publication. But over here I have the full graph of the attack. No data is missing. I could see that, after Netcat was launched, they dropped a rootkit, which was then later executed. They then made connections to various IP addresses. They read some data. That data may have been exfiltrated, et cetera, et cetera, et cetera. And then a lot of other interesting work occurred around developing policies that actually leverage provenance and flows. So in the literature, this is a problem of full systems provenance. So for example, you could write policies, security policies, that aren't pattern matching against system calls and paths, but are instead focused on the flow of data. Trigger an alert if medical data has been read or potentially been read by an application, and that application then connected to the network. In some cases, you might be able to directly tell that, hey, medical data was exfiltrated, but at least you can always rule out whether or not it occurred. This is huge also for compliance purposes, right? Are you in breach of GDPR, PCI, yada, yada, yada? These systems allow you to do that.
Like 5 minutes ago.
Okay. Again, bit of background here. If you're interested in this, this is a problem of full systems provenance. So one of the first systems there was Hi-Fi. Several years later, Adam Bates created Linux provenance modules for Linux. Several years later, and probably the most popular system was University of Cambridge's CamFlow project. And there's still some interesting work coming out of that. The idea is, what if you could augment an operating system to be able to collect this provenance data? So the first challenge is it practical? That's a lot of data. Every single file read, every single file read, written, it's a lot of data. So, basically where literature is today is not really, right? But this has been being revisited. Stony Brook has done a lot of interesting work recently. Gabe and I have been working on this as well. So this is a pretty cool paper. They focused on what if we could make eBPF data collection fast. Unfortunately, there are always biases. The data collected is insufficient for an actual security product, but there are some very cool techniques and results here. So over here they ran the provenance system from literature. They ran, this is actually a security product that I was testing, so Systex Falco. They configured audit D to provide the same level of logging, and they measured the slowdown and performance overhead. I won't dive into it given that we have now less than 5 minutes, but long story short, you can see an example of audit D when they ran a benchmark called postmark, which basically just creates and deletes and writes thousands of files a second. It had a runtime overhead of 654%, right? So it's pretty expensive. So where are we today? So we're working on solving this problem. It's two issues, right? How do you ensure that it's low latency so you don't impact performance as much on production workloads? And then the other big problem, which actually isn't touched on as much, is storage. How do you store this data, right? So for example, if I run a 10-second work benchmark, and in this case, just out of laziness, it was many months ago, you run strace on it, you gzip compress it, it's 30 megabytes every 10 seconds. So on heavily loaded systems that are leveraging a lot more interesting syscalls, et cetera, that's going to be a lot larger. Again, this is over 10 seconds. You're talking about hundreds of gigabytes or terabytes of data a day. So in the case of work, it's 259 gigabytes of compressed data a day. It's just not feasible in production, right? So I think today we're at a point, and actually literally today, a lot of hacking going on lately. Is it practical? Probably. There are some pretty great promising results, and we're still working on this. There are little performance optimizations made after this. So over here, we run work against Lighty, and you could see Vanilla, which is basically a Linux system without any kind of observability tooling. And then Systex Falco and Tetragon. And then you see BitBison here. So The way this comparison is also made is if you want full provenance data, you need to have that granularity of data. So Falco and Tetragon were also configured to log extremely high granularity data. Not the same granularity at us, but close, right? And again, but there is a performance impact, but for many production systems, especially if they're not in an overloaded state, it's acceptable. So just consider it in your COGS model. And then the latency impact is negligible, right? Unless you're in the microsecond scale, like if you're in high frequency trading, there are certain hooks you'd want to disable. But generally speaking, for most workloads, no meaningful impact. Linux kernel build, we go from 22 seconds to 24 seconds. Falco goes up to 31, Tetragon goes to 39. Cool. And the worst workload is Postmark, especially for the data model that we're using, et cetera, which we will make public. And we're also considering making this open source. We're still thinking through it. It's early days, open source and free, because EDR is in a weird state today. But Postmark is the worst case. We go from 361 to 1095, still significantly better than the technologies available today. This is better as a result of some optimizations we made today, and we continue to work on this. So very promising results. Storage is where you see also the biggest gains, right? So that work benchmark, which was 30 megs of compressed, S-trace data, is 0.01 megabytes. So these are fundamentally, we're speed hacking, speed running IDSs, right? So yeah, that's where we're at. It's still early days, and hopefully, I hope this was useful, and I'm excited for us to go public with this. But we're taking our time with the engineering. He's a professor, and I had an exit a few years ago, so we want to solve the problem, and we're serious about it. So yeah, any questions?